Good morning everyone. Today I'll be talking to you about user datagram protocol, commonly known as a UDP. It's one of the core protocols used on the internet and it's play a vital role in fast and efficient data transmission. This presentation will cover the definition characteristics of UDP, its header format and checksum mechanism, the process of sending and receiving data, key difference between UDP and TCP, and application where UDP excels, security concurrence and future development in UDP. First, what is UDP? UDP is a connectionless protocol. This means it doesn't need to set up a connection before sending data. Think of it like a sending postcard. You write your message, drop it in the mailbox and hope it reaches destination. We don't wait for a reply before sending the next one. That's how UDP works. It sends packets called datagram without checking if they arrive. This makes UDP very fast. It's like taking the express lane on a highway. You get to your destination quickly, but there's risk you might miss an exit because of its lightweight nature. UDP is often used when speed is more important than reliability. Some common use cases include streaming video or audio. Would rather have a few glitches than wait for every bit of data. Online games, real-time action is key. Even a slight delay can the experience. DNS next. A domain name system. When you type a website name, DNS quickly converts it into an IP address. We need this to be fast. So UDP is all about speed and efficiency, even if it means sacrificing a bit of reliability. Next, let's look at what a UDP bucket or datagram look like. Each UDP packet has a simple header with just 4 fields, each 16 bits long. First, short port. Identify the sender's port and next destination port. Identify the receiver's port and length. Specify the total length of a bucket including the header and data. Next, checksum. Help verify and data integrity. It ensure the packet wasn't during transmission. Because this header is so small and simple, UDP is faster than other protocols like TCP, which has a much larger header. Next, let's talk about the checksum field in more details. Even UDP is fast and simple. It doesn't ignore data integrity. The checksum is used to detect error during transmission. Here how it's work. First, pseudocode header. Some file fields from the IP header are added temporarily to help with checksum calculation. Next, calculation. The checksum is calculated by using this, the UDP header and data being sent pseudocode header. Next, verification. When the receiver gets the packet, it's recalculate the checksum and compare it with the center's checksum. If they match, their data is correct. If not, the bucket is discarded. This process is like double checking a bill at restaurant. You add up the item and compare them with the total to make sure there is no mistake. And next, UDP communication process. Let's break down how data travel using UDP in simple step. First, application sending data. The application sends the data to UDP layer. Next, UDP encapsulates data. UDP wrap the data with header, creating a datagram. Next, IP transmit packet. The bucket is handed to the IP layer, which is sent it over the network. Next, receiver process data. The receiver's UDP layer extract the data and gives it to the application, and there is no handshake and no acknowledgement, and if the data is lost, it's gone. But this is exactly what makes UDP so fast. And next, UDP versus TCP. At the point you might be wondering how it's UDP from different TCP. Let's compare them. First, UDP is like sending a postcard, while TCP is like making a phone call. TCP ensure world is had, but it takes time. UDP just send the message and move on, which perfect when speed matter more than accuracy. And next, application of UDP. So what do we actually use UDP? Streaming. First, streaming service. Watching a live cricket match, we want fast updates. A minor glitch is okay, but delay the experience. Next, online games. Real-time actions need speed. If a player moves, everyone should see instantly. And next, DNS, domain name system. When we type google.com, we need a quick response. UDP gets it's done fast. This application prioritizes speed and low latency of over perfect delivery. And next, UDP program. Examples. Here sample Python program to demonstrate a UDP server. This program listens on port 5005 receive data and prints it simple and fast, just like UDP. And next, security concurrence. No congestion control. If data flow is too high, it scares network congestion. No security features. Data can easily intercepted from spoof feed. And next, to mitigate this risk, we can use encryption. Encryption protects data from dropping. Additional security protocols like DTLS. While UDP is fast, security measured must be had separately. And next, future trends. Future trends. UDP is not standing still; it's evolving to meet the demands of modern technology. First, QUIC protocol developed by Google. It combines UDP speed with built-in security and reliability. Next, low latency improvement. Perfect for real-time applications like video call and cloud gaming. Next, better reliability. New techniques are improving UDP's reliability without sacrificing speed. So UDP is adapting to balance speed, security, and reliability. Next, conclusion to wrap up. UDP is fast and connectionless, making it ideal for streaming and gaming and DNS. It has a simple header with a checksum for basic error detection. It trades reliability for speed, unlike TCP, which is slower but reliability. Next, security is concurrent, but encryption and modern protocols like QUIC are addressing this. So while UDP is simple, it remains crucial for real-time applications, and as technology advance, UDP is evolving to stay fast, secure, and reliable. Thank you.